I want to talk today a little bit about ZFS replication in the context of backups. ZFS replication seems like a really excellent way to do backups. It's fast, it's really easy to use, and it's pretty secure. And it's a lot faster than doing rsync for like doing incremental backups. And one feature that makes ZFS replication particularly compelling is that you can have an encrypted data set, an encrypted file system on the host that you're trying to back up from, and send over the wire that encrypted information and keep it encrypted at rest on the target machine, and then do incremental backups that will also send encrypted data across the wire and keep it at rest encrypted. And it's pretty great. In this video, we're going to use OpenZFS to make a backup from a local system to a remote system. And we'll do that for both encrypted and unencrypted data sets. And I'm using OpenZFS here. That is an implementation of ZFS that is available for Linux, FreeBSD, IllumiOS, and I think there are pre-alpha or alpha or beta or some combination thereof of releases available for Mac OS. I know that the Windows version is definitely pre-alpha. There's a Windows version. This differs from the canonical version. Well, I shouldn't need to say canonical, that's another company name. This differs from the Oracle version of ZFS. OpenZFS differs from that in that that tends to, I think, only run on Solaris. I'm not entirely sure about that, but the OpenZFS stuff is born of the Oracle ZFS stuff, which was born of the Sun ZFS stuff. And this stuff all started somewhere around the year 2000 or so, and it's been through a number of owners. Sun birthed it, Oracle now owns it. The OpenZFS folks took a earlier version of a freely available version of ZFS that had been released when Sun still owned it. It's under a license called the CDDL, and they've basically forked that from the Oracle version. So they're proceeding along parallel tracks. Both are excellent file systems. They're not just file systems. ZFS is at least three things. It is a file system, it is a volume manager, and it is a pool management, disk management system. And a fourth thing you might consider it to be would be a way of producing streams that represent changes to your data sets over time. So, and that's what we're going to look at today. So a little bit of information about the setup here. You can tell by my very attractive, people make fun of my yellow terminal windows, but I love them. We have two systems. We have a system named ThinkM on the left and a system named M82 on the right. And I'm logged in as the Chris M user on both of them. They're actual physical machines. They are sitting near my feet. And for purposes of this demonstration, ThinkM we're going to consider local. That'll be, sort of hold the data that we want to back up. And M82 will be considered remote. We have SSH private key login set up between ThinkM to M82. So I won't be typing any passphrases. We're going to use SSH a lot to do these encryptions. And there goes my air conditioner. I'll be right back after I shut that off. All right, sorry about that. As I was mentioning, we have SSH public key login set up between these machines. Both of these machines are Ubuntu machines. They're both running Linux. I think one is a slightly older version. I think one is 1804 and one is 2004. But both of them are running 0.8.x versions of OpenZFS. And for all intents and purposes, they're completely equivalent to each other. The first thing we're going to need to do in order to demonstrate how ZFS replication works is we're going to need to make a data set. And we're going to make that on our local system, quote unquote, our ThinkM system that we're treating as our source. And we're going to create a data set. Now, I already have on both of these systems, on both ThinkM and M82, I already have pools set up. I suppose I should show them. ZFS List. Z. On ThinkM, there's a pool named Z. And on ZFS List. And on M8, my 2 key is having problems. On M82, there's a pool named Z2. And right now, we're not going to worry too much about the destination. We'll deal with that later. We're going to do most of our work on the local machine here. And so we're going to make a data set, which you can think of as a file system, more or less, on our ThinkM system here. We're going to use ZFS create Z source. I should just paste this in, didn't I? I should just paste it in. Sudo ZFS create Z source. And my disks need to spin up. They're in a USB enclosure. Not exactly data center standards around here. So now what we've done is we've created a file system on our local machine, which is represented here at Z source, and it is mounted already. That create command mounts it by default. And that we can put files inside of that directory now, and we can treat all the files that exist in that directory and any subdirectories underneath of it as a unit, and we can back that stuff up. So I'm not going to show how to create pools. That's sort of a layer below this. I will link to an excellent description about how to do that in another video. So now that we've created the data set, let's add some files to it. Z source. And I came up with some, one other thing I have to do before I just preserve my sanity. I have to change the owner of Z source to me so that I can make files in it without sudoing. Otherwise, it would be owned by root. So I have this really crappy bash for loop that creates 10 files. 0 through 9.txt, and they have a little bit of content in them. They each have 5 bytes in them, and we'll take a look at what that looks like. 0.txt has 4 zeros or 5 zeros in it. 9.txt has 9 zeros in it, and everything in between. So essentially, we have 50 bytes of data in these files, and so this very important data needs to be backed up now. And the first step that we will take before we can back up anything is we need to make what's called a snapshot. And a snapshot just represents the state of the data in this file system at a point in time. And it's really easy to do. We just do something like sudo ZFS snapshot Z source, and then we're going to give it an @ symbol, and then we're just going to give it a tag. We're just going to use the number 1 for now. It doesn't really matter. And you should note that this operation, for any amount of data that you're going to care about, probably certainly that I'm going to care about on my ghetto USB enclosures, this operation, the ZFS snapshot, is essentially constant time, no matter how much data you have. We happen to have only 50 bytes in here, but I think even if I've run this command on much larger data sets, and it doesn't seem to take much longer than that. Terabytes of data. And so anyway, let's go over to our M82 machine and just get a list of data sets that already exist. Now, since I did that, I'll do this on this machine. I'll do ZFS List, and I need to, ZFS List Z doesn't quite do it. And I need to pass in a flag. Type all. Oh no, I gotta pass it in first before that. ZFS. Type equal all. Is that right? I should just paste it. I have it here. Don't I have it here? ZFS List. T all. Okay. Yeah. Oh, for heaven's sake. Z. For whatever reason, I think I don't quite understand this. I would expect that if I was just listing stuff that is in Z, that I wouldn't need to pass this -R flag. Maybe that makes sense. I guess that makes sense because it really is a descendant of the thing. Anyway, I'm talking to myself now. But in any case, on this machine, you can see that we have. I'm going to just use the -R, and we can see the actual data sets that we have here. We have source and storage, and then we have the root, which is also considered a file system, but we don't actually put any stuff directly in there except these doodads. So I actually have another data set in here that's called storage, and that's my actual data. That's the actual data that I care about. And we're just using the source data set as a test bed. So over here, we'll do the same thing. We will I should mention that the things that we saw up here, these are snapshots, and they represent a point in time, but they are considered data sets from the point of view of ZFS because they represent a data set. They are all the data about a data set just at a point in time. So the main difference between those is that you can mount a non-snapshot as read-write, but you can't mount a snapshot as read-write. It's read-only. On the other machine, we can do the same thing. We'll do copy Z2. My 2 key is really having some trouble. Now notice over here. Now I've done a replication of my really big, 5 terabyte, 4.5 terabyte storage here between these two before. So these are actually pretty much the same thing. But you notice that we don't have a source over here, and the storage thing is irrelevant to us. That's my own data. It has nothing to do with us. So the point is that in order to replicate the data, we don't actually have to, SSH to the machine that's hosting our other ZFS storage and sort of prepare it. And, well, we do, but we don't have to prepare the actual data set. We're going to create it as a result of the send. So I'm going to get smart and start cutting and pasting things. So the command that we're going to use to do replication is a combination. The two commands we're going to use to do replication are ZFS Send, and that'll run on our ThinkM or local machine, and then ZFS Receive, which is going to run on our M82 or remote machine. And the way that this works is that this command right here, ZFS Send, z/source at 1, will run here, and it will produce a stream. It'll just spit stuff to standard out, and that will be piped to SSH, and SSH will receive the stream. It will log in. It will log in to M82, and it will then execute the ZFS receive over here. And if you notice, we are sending, this is the first time that we do a ZFS snapshot or ZFS replication, we're sending the entire data set. There's no incrementals, of course, because there's not anything to increment. So we're sending the snapshot we just made from our source, and then we're just sending to a target data set over here. Now, target data set does not exist yet, but we're going to create it as a result of doing this. So I'm going to do this. This is going to fail, and we'll see how to fix it in a second. Okay. Permission denied. I can't send Z source 1. All right. So, and then the other thing's complaining to me that it cannot receive. We're going to fix this by using a command called ZFS allow on our ThinkM machine. And we are going to give the ChrisM user, just cut and paste it, Chris. You don't have to do anything else. We're going to give our ChrisM user 2 permissions, 2 ZFS permissions. We're going to let him send things and make snapshots. I think really the only thing we need to let him do here is send, but it's just convenient to be able to make snapshots as ChrisM. So I'm going to give him that permission over here too. USB enclosure is spinning up. Good, 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 good. And so let's give it a shot again. Now this is also going to fail. Yes. So permission has been denied for receiving it. So what happened was that this command got run over there, and it ran into that problem. So we need to go over to the remote system, and we need to give our ChrisM user there a different set of permissions. Now, I've cargo culted some of these from various places. I'm not sure if these are all required, but I'm imagining the compression is required because we're going to use compression in the stream later. Create, I know, is required because we need to create a data set. Don't really think ChrisM needs mount permission here. It's just convenient. And we know that he needs receive. I'm not sure. I'm not even sure what mount point is, to be honest with you. I cargo culted a bit of this. So I think the permissions that actually probably matter here are compression, create, and receive. In any case, just for ease of demo, I'm not going to stray from the script. Okay. So at this point, we should be able to run this command on the system, and it should do our first full send of our incredibly important 50 bytes of data. And it did. How about that? Okay, so now that's really it. That's really it for backing up. You know, it's not very impressive because you could have done the same thing with a CP-R and or a scopy or an rsync or anything. But as we can see, now when we do there, we have a target, and we have a target data set that bears striking similarity to the source data set that we have up here. It's 104K. And we notice we also have a snapshot, and it's a snapshot at 1. So when we do this, we are essentially we're gonna have a mirror image from source to target of all our snapshots. There's only one snapshot in there right now. It's number 1. So we can see that this actually worked. Oh, by the way, I should mention this command, this little flag here to ZFS receive, this -u. What it does, I'm going to just do this again, just because I'm sudo. What am I trying to do? ZFS destroy. ZFS destroy Z2 source. No, target. And I need to -R. So basically what I'm doing is just blowing away what I just did. It's not a big deal. If I do not pass this flag, what happens is on the creation of the data set on the remote side, it automatically tries to mount it. And for whatever reason, I cannot figure out the set of permissions I have to give this. I have to give Chris M on the other side. I gave him mount point. I have no idea. For him to be able to successfully mount it. Root can mount it fine, but Chris can't. So we just pass the flag that says don't try to mount it because we don't care. We're making a backup. We're not actually trying to get something mounted over there. So I'll just show you what happens if I do that. Now it actually works. It just has this error in it, which is just ugly. But it actually did the same thing. It just couldn't mount it. Anyway, let's go over here and we will mount our target. I think, is that what we want to do? Yeah, let's do that. Sudo ZFS Mount Z2 Target. And now we can go to Z2 Target, and we can see that it has the data we expect. Well, we can see with my fancy script here that it has the data I expect. Indeed, same data. So we've done our first successful full replication. Now, I think one oddity to this, I think if we try to, I'll deal with that later. We'll deal with that later. That's basically all there is to a full backup. Now, unfortunately, the default arguments to ZFS Send are geared more towards compatibility rather than speed. So ZFS Send takes some optional arguments that turn on stream compression and turn on a number of other speed features that you probably want to use. These days they probably should be the default. As far as I understand it from the OpenZFS developers, they should probably be the default. But this is just, this thing's remarkably streamlined for being 20 years old. It's hard to fault any of it. It's just really got a really great user interface, and oh man, it's great. But let's destroy our target again. We just like destroying. Destroy. Okay. And this time, I'm going to use a few flags to the ZFS Send command. And they will be compression, which is C, E, which is some sort of embedded speed thing. I'm not going to pretend to understand it. L for large blocks, also no clue. These are just kind of like the stream format stuff is smaller when these flags are passed when generating the stream. And we're also going to pass this this V flag because that'll give us a little bit of feedback when we on our standard out or standard error on our sending side as we do these sends. So I've already destroyed the target. We're good to go again. Boom. Okay. Now, oh, I forgot to yeah. Anyway, it worked. You remember. So at this point, we can mount it again. And Z2 target. Sure enough, same thing worked. So we did get this. One visible thing that we can see that changed is that we got some stuff on standard out here that helped us, that gives us some sort of estimate about the size of the stuff that it thinks it's sending. So just for fun, let's see whether its estimate is is more or less correct. So we don't need to actually pipe this. This is just Unix. So to out and du list out. So it thought the stream was going to be 43.6K, and it's more like 57K. I'm not sure. Not sure what the difference is. I have a bit of a side note about that in a little bit, but it deals more with encryption. It's actually the inverse result. When there's encryption involved, the estimate is too big. In this case, the estimate's too small. Don't know. Anyway, I just think that's interesting. Now let's put some more data in our source directory here, and we will add 10 more files, 10 more very important files to our source collection here. Now we should have 0 through 19. So we have 20 files in here, and the new files, they're not just 5 bytes, they're 10 bytes. I know they're 10 bytes a piece. And now let's make a snapshot of that. No, I don't think I need to use sudo for this anymore. Snapshot z/source at 2. Indeed. And I'm sure I don't need to ZFS list that to prove to you that that worked. And I'm going to just unmount this thing over here because there's no particular... Oh, maybe I'll try to leave it mounted. Why not? We'll see what happens. At this point, we can do an incremental send. And the incremental send that we do is going to represent the set of changes that happen between snapshot 1 and snapshot 2, which in our case was the adding of 10 files. And the difference is that the send side of this command takes slightly different arguments when it's an incremental send than it does when it's a full send. We'll take a look at that. Okay, so we're going to use our go fast flags, the CEL and V, but then we're going to pass this additional flag in to send, which is -I, and that takes an argument, and the argument is z/source at 1. That is the snapshot that represents the point in time that we want to consider changes from, and then the final argument, which is z/source at 2, is the snapshot that represents the point in time that we want to send changes, consider changes to. So, the difference between snapshot 1 and snapshot 2 is what we want to send. That's what basically this is saying. That is a much easier way. That's a much better way to say that, Chris. The receive command does not change. Has nothing different about it. So I think this may fail because I think our mounting of the target may have disturbed the force on the other side, but we can fix it if it does. So I'm gonna give it a shot. Can I send? I don't think I need any. I don't think I need sudo here. Oh wow, it worked. Okay, cool. Very cool. Okay. Yeah, I didn't need to unmount. That's really good. So at this point over here, oops, C2 Target. Yeah, we have our 10 files. We do have our 10 files, and we can see that they're the same on both sides. Hold on. I know it's pedantic. I get it. Hang on. Just whoa. Hold on, buddy. Yeah. Sure enough, all the same. So that is really about it for ZFS replication. That's about it. The rest is all just details and gravy. The interesting bit is that when we did our incremental send, if you notice here, it says the total estimated size is 34.1K. I wonder if that's accurate or not. Let's just see. It's 20K. I don't know. So still overestimating the size of the thing. Now, you might be saying, Chris, I thought you told me this thing was fast and efficient, and all we did was we created 100 more bytes of files in there, and it's representing that with 20K. Are you off your rocker? Well, here's the thing. What it's sending is it's not like rsync. It doesn't actually send files. rsync does a pretty good job. I don't really know exactly how rsync works, but I think it tries its best to like send the least amount of data possible, but it also has to walk the file system to do that. And if it can't figure it out, it has to resend the whole file. So if typically, the thing that happens all the time is like maybe a virtual machine image will change or something, and it's like a 1 gig file or something. And if any byte in it changes, it's just got to send the whole file again over. That is not at all how this works. This actually works by sending a representation of the blocks, the literal file system blocks that were changed by virtue of the stuff that happened between these two snapshots. And those blocks are larger than 10 bytes. And I think each one of our files took up a block in there. And I think I'm not entirely sure how big the block would be that created, but it's anywhere from 512K to 512 bytes to 4K, something like that per file in here. In any case, it's basically replicating what we did between those two snapshots in terms of what happened to blocks on disk, and sending some representation of that across the wire. And that is just much larger than 100 bytes. But for big, very, very big files, it is not. And just to prove this, let's put a big file in here. Now this is an ISO. I think it's like 2 gig or something. 2.4 gig. And let's make a snapshot now that contains the unmodified ISO. After we take the snapshot and transfer it over, I'm going to make a change to this to some binary data inside of the ISO, and we'll do another sync and see what happens. So what was the last snapshot we did? ZFS snapshot. Okay, I'm going to get rid of this out file. We don't need that anymore. Out. Source 3. Okay, now our 3 snapshot knows about our new ISO. And we can just rerun our ZFS Send. If I can find it again. There it is. I need to change anything? Yes, I need to change these 2 arguments. I need to go not from 1 to 2, but from 2 to 3. Send me the changes between 2 and 3. Put them on our Z2 target. Okay. So basically, this is just like a copy. There's nothing magical going on here. It's going to take a bit, probably about 30 seconds. And this, you know, obviously this chain of snapshots just keeps happening over time, and that's how you make backups. That's about it. The one thing I haven't shown so far is encryption, which we'll get to in a second, which is actually the icing on the cake. It's sort of the killer feature of this thing, I think. So now that we did that, can we see it on the other side? Yes, we can. So we have it on the other. I am going to use my elite hacking skills. I'm going to put 2 Python scripts in our source directory too. One we're going to call print ISO. I don't need edit. I need VI. And what this script does is it opens our ISO file. It seeks to about 1 gigabyte in the file. It reads 10 bytes. And then it prints a hexadecimal representation of those bytes. Now, pardon me for using Python 2. I know. But I'm sure someone will give me a hard time for this. We have another script that is also a Python script that makes a modification to those same 10 bytes that we printed out in the file. We'll see why that's useful in a moment. Change ISO pi. Okay. So we can see that this thing opens the same file, but it opens it in write mode. It seeks to the same position that the other script did, and it generates 10 random bytes, prints them to the console, writes them to that one spot, and about halfway through this ISO file, and then closes, and everybody's happy. And first thing we're going to do is against our sources. ISO file, we're going to print what used to be there. This is the unmolested data stream. These are 10 bytes that existed before I make any change to this thing. But once I run change ISO.py, now nothing has changed. The only thing that's changed in our source data set is me adding those 2 scripts. But the ISO file has not changed until now. So now we've made a change to 10 bytes within the middle of a 2 gigabyte file. And we can make sure that it's actually effective by printing yes, it printed the new bytes. So we're going to go back to our old friend ZFS snapshot. And we're going to call him 4. Okay, and then I think we can just do our send again. That's our incremental send. We want to send the changes between 3 and 4. That didn't take very long. That certainly didn't take 30 seconds. So you can see that in reality, even though the stream size seems a little inflated, that the algorithm works out in our favor. In any real world situation, this thing will beat the pants off rsync, because it's not that rsync is bad. Rsync is wonderful. It's just that rsync has none of the information that this thing does about which parts of files changed. You know, what we're trying to do. You know, by syncing between 2 snapshots. None of it. It's just gotta plow through all the files, you know, anew every time it runs. So this doesn't need to do any of that. This knows this snapshot has these modified blocks in it. Those are the blocks I need to send. Done. So we can tell just for fun over here. We can tell we got our print ISO pi. Ubuntu Mate. Oops, that's not what I want to do. Print ISO pi. And indeed, our snapshot, our bytes are the same. So anyway, replication works. This is all very cool, but both on our local system and on the remote system, this stuff is kept decrypted. And it's really easy in ZFS to create encrypted data sets, and it's really easy to replicate encrypted data sets. We're going to do that. In order to do that, I'm going to destroy again our target here. And I'm going to destroy our source too. Destroyer of worlds. Destroy the source. Oops. Okay. So now we are more or less at the point where we started when I first started this video. The only difference is that this side over here, when we did this ZFS allow up here, we didn't do it against a data set. We did it against the pool. So the thing that we just deleted with the ZFS destroy over here did not contain the changes we made to this pool. Those will remain. So we don't have to make those changes again. We will have to do it on the other side because we only gave Chris M permission on this particular data set to send and make checkpoints. But more or less, we have started over except for that one new. So this time it's going to be almost exactly the same. We are going to ZFS create a data set, but we are going to create it with some encryption flags. And we're going to use the AES-256 GCM cipher. We are going to tell it to use a passphrase as its wrapping key source. And I just use a OpenZFS internal jargon, but there's actually an encryption key that is stored along with the data set, and it's sort of like an SSH key passphrase that unlocks that encryption key. When the thing we're typing in here now is the thing that will actually unlock the encryption key. The encryption key is actually sent along inside the data set. It's just that you need this additional level of indirection passphrase to unlock it, and it unlocks all the stuff that's in the data set. So that actually works out really well for this because we'll see. I'll show you. So trust me, all that stuff is required to create a data set that is encrypted. Okay, now we have exactly the same scenario here. We have a z/source, and it looks exactly the same. And we're going to do the same thing again. We have to rechown our source here. Otherwise, I'm not going to be able to add files to it. And then we're going to do the stuff where we created these files in here. Same thing, the 0 through 9 files. And we're going to do our snapshot again just because we've done all this before. And again, we need to redo this part of the permission setting that we did before because we created a new source data set. Okay, so we saw before that ZFS Send worked just perfectly fine, but you can imagine some weirdness like if somebody asked me to send an encrypted data set, what does that even mean? Like, do I send the encrypted part of it, or do I decompress and then send the stream? Well, the answer is that without this flag I'm about to give it, which is -W, otherwise known as raw send, ZFS Send will, in order to compose a stream, will decrypt the data and send it all as a normal send. When it is when we pass the flag in, let's see, visual cue here. Before, our other command just did this. There was no -w, and W means raw send. Once we add that W in there, that means that we are sending just the raw bytes. Is basically just taking the stuff that's on disk, no matter what it is, whether it's encrypted or unencrypted or what, and it will pack that stuff up into the stream. And I think this will work. Yep. Okay, so now we just go through the motions of our encrypted, our -I. We got to go through the same motion of. Oh, I suppose we should add some files. Yeah, that's what we should do. Add some files. We're going to add 10 through 19 in here now, and we'll make that part of snapshot 2. Good. And now we can try our incremental send between 1 and 2. But we have to add that -w in front of here. Doesn't really matter where it goes, but it's got to go somewhere in there. And this is from 1 to 2. Yep. So there we go. It did it. Now, trust me, I've tried the big file send, the same test with the ISO, and it has comparable performance. It does not send the whole file again. It was just as fast as the other one was. The difference in this case, however, though, is that if I try to go over here and do sudo ZFS Mount C2 Target, it just bundled the stuff up. Like it's just a big blob on disk. The person, like if there's another administrator of this system, let's say it's somebody you don't trust, you shouldn't trust anybody with your data, but if it's somebody that a vendor, or something that you're buying backup services from, you don't necessarily know those people very well. You give them money, but you don't want them snooping through your stuff. But you can just send this stuff up there. They can't get into it without the passphrase, and that's really nifty. But you can. Is it load key? ZFS load key. Z2 target. Yeah. Now, if I try to mount it, it works. It's so cool. It's just really bitching. It is wonderful. So that's about it. I'm a fan. I tried. I have this other set of this storage thing here, and I sent the initial send took like 9 hours over a wireless network connection for about 1.5 terabytes of stuff, and then I had an additional like 400 meg of stuff later, and that took I did an incremental send of that, and it took about what you'd imagine, but then I made a couple changes here and there on stuff that was in that directory, and it took no time whatsoever to do that incremental send. So it is just a wonderful tool. I'm super impressed by this thing, and I sort of lament that I am a Linux user because what happens is all this cool technology gets invented 20 years ago, and I just utterly ignore it. Like I'm just a typical Linux user. Just like, is it in Linux yet? It's dead to me. I don't care. But since ZFS has gotten onto Linux, which has only been in the last, I don't know, maybe 8 years or so, maybe a little bit longer, and really it hasn't been very widely used on Linux by anybody until recently. And even now, I wouldn't say it's widely used, but it's at least used. I mean, the FreeNAS people who base their storage device or their NAS device, they historically been a BSD company, and they run ZFS. And that device is fairly popular. It's a piece of software you can download it yourself, but they also sell boxes with it already installed on there. But they've started to make noises about, supporting Linux. Linux and BSD are peers now. Like they're both going to be supported. I think we know how that's going to go. This stuff has been around in Solaris and BSD forever, and I just didn't know. I feel embarrassed. Really great stuff. There is a company, one company that I know of. There should be like at least 10, at least 20, at least 100 companies that offers commercial ZFS replication target accounts. Basically, it's just a shell account, and you can do what I just did. You send them do ZFS Send and pipe that stuff to their pool. I cannot vouch for them. I don't know anything about rsync.net, which is the company that offers them, but they seem to be the people that do this. So if you wanted to try to use XFS and do incremental backups over your network and have it encrypted, that would be a way to go. Many thanks to a guy named Don Ware, who goes by the nickname DJ. DJ Ware. He is the one who turned me on via a YouTube video of his to ZFS, and only because it was like ZFS on Linux. And I watched it, and I was like, wow, that's amazing. So I'm going to link it, give a link to his video in this description below. And thank you. Thanks for watching.